Okay, imagine this for a second. You're just floating out there, deep space, and you look back, and there's our whole galaxy, the Milky Way,
Yeah.
just kind of drifting along inside this giant, mostly empty bubble.
Hmm.
Not totally empty, but way less dense than everywhere else, a cosmic void.
Right.
Sounds a bit like sci-fi, doesn't it? But, well, this whole image, this idea, might actually be the key to solving one of the biggest puzzles in cosmology right now.
Yeah, the Hubble tension.
Exactly. It's this major headache that scientists have wrestled with for years, and this void idea. It would finally be the answer. So our mission today in this deep dive is to really unpack the evidence for this, see what it means for how we understand, well, everything, the whole universe.
And it's worth stressing, just how big a deal the Hubble tension is for cosmologists. This isn't some small rounding error we're talking about. It's a persistent disagreement. It's really challenged our standard models.
Right, our basic understanding.
Precisely. So finding a potential solution, like this void theory could be, something that maybe bridges that gap, that's genuinely a huge development.
Okay, so let's get right into it then. What exactly is this Hubble tension? It boils down to the Hubble constant, right?
Yeah.
Which is just the speed the universe is expanding at.
Mm-hmm.
And the tension, the research calls it an heretofore irresolvable discrepancy. That sounds serious. They even call it the most exciting crisis in cosmology.
It is quite a title, but it fits. Because the core issue is we have two main ways to measure this expansion rate, and they keep giving us different answers, consistently different.
Okay, so what are the two ways?
Well, first you've got measurements based on the really early universe, things like the cosmic microwave background, that sort of leftover heat from the Big Bang, and also something called baryon acoustic oscillations, which we'll probably get into.
Okay, the early universe stuff. What number does that give?
That method gives a Hubble constant of about 67 kilometers per second per megaparsec. Remember that number?
Yeah.
67.
67. Got it. So what happens when we measure things, like closer to us in the more recent universe?
That's where it gets tricky. When we use methods based on closer objects, things like type A supernovae, those exploding stars, or Cepheid variable stars, these are like standard candles, really crucial for measuring distances nearby.
Right, the local measurements.
Yeah. Those give us a different number entirely, around 73 kilometers per second per megaparsec.
73? Okay, wow. That's not a small difference from 67.
Not at all. 67 versus 73, that is the Hubble tension. It's like, having two incredibly precise rulers, but they give you different lengths for the exact same table, and nobody could figure out why.
Until maybe this void idea steps in.
Mm.
You mentioned cosmologist Indra Banach proposing that our galaxy is near the center of a large local void. So the big question is, how does sitting in a void solve this 67 versus 73 problem?
Right. Well, the key is understanding what a void is. It's not a perfect vacuum, not completely empty. It's just a region where matter is significantly less dense. The sources say about 20% less dense than the average volume of space compared to, the big clusters and filaments of galaxies elsewhere.
Okay, less stuff there, so.
So gravity does its thing. It pulls matter out of this less dense region towards the denser stuff surrounding the void on the outside.
So the void is actively getting emptier.
Kind of, yeah. It becomes emptier over cosmic time. And here's the clever bit. If we're inside this region that's emptying out, then things around us, galaxies and so on, will appear to be moving away from us faster than the overall cosmic expansion rate would suggest.
Like we're on a raft being pushed away from the shore faster than the current alone would carry us?
That's a decent analogy. Or the treadmill idea mentioned earlier, you're walking, but the treadmill itself is also moving backwards, so your speed relative to the room seems faster. This gives the appearance of a faster local expansion rate, which could explain why we measure 73 locally, even if the true background rate is closer to 67.
That actually makes a lot of sense. It's an effect of our specific location.
Exactly. And people had suspected this before, hints that maybe we're in some kind of underdense region, maybe 2 billion light years across. But it was always seen as far from proven until this new work.
So what changed? What gave Banach and his team the confidence to really push this theory? How do they actually test it? What's the new evidence?
Great question. It comes down to finding something measurable that would confirm this void's effect. And the key, according to their research, is in these things called baryon acoustic oscillations, BAO for short. They're described, quite poetically, as the sound of the Big Bang.
The sound of the Big Bang. Okay, you have to explain that one. What is that, and how does it help prove we're in a void?
Okay, yeah, it sounds weird, but think back to the very, very early universe. It was. Well, the source says, just a wee baby, full of nothing but sloshing plasma. Hot, dense soup of particles and radiation.
Right, this primordial soup.
In that soup, gravity was pulling matter together, but the intense radiation pressure was pushing it apart. This cosmic tug of war created essentially giant sound waves, ripples of pressure spreading outwards through the plasma.
Like throwing a pebble into that cosmic pond.
Exactly like that, huge ripples. But then the universe expanded and cooled enough that the plasma turned into neutral atoms. Suddenly the radiation could travel freely, and the pressure waves, they couldn't propagate anymore. They basically stalled. They got preserved as vast spherical arrangements of cosmic structures with higher densities of matter at their edges.
So these ripples just froze in place, leaving behind shells of matter.
Pretty much. They're the fossilized sound of the Big Bang, a buzz trapped in time. And we can actually see their imprint today as faint patterns in how galaxies are clustered, these sort of giant ring shapes in the cosmic web.
Wow.
And here's the crucial bit for measurements. Because of the physics involved, these rings, these spherical shells, all froze at the same size, about 1 billion light years in diameter.
A standard size. Like
Yeah.
having identical rulers scattered throughout the universe.
Precisely. That fixed size is incredibly useful. If you know how big something should be and you measure how big it looks in the sky, you can figure out how far away it is. BAO gives us a standard ruler for cosmic distances.
Okay, that makes sense. A cosmic standard ruler. So how did Bannock's team use these BAO rings to actually test the void theory? What were they looking for?
Their hypothesis was clever. They thought, okay, if we're in a large void, that void's gravity, or lack thereof, relatively speaking, should subtly distort how we perceive those BAO rings. It should create a specific kind of measurable distortion, especially for rings at different distances. The effect should be stronger further away.
A predictable distortion signature.
Exactly. So what they did was they carefully re-examined 20 years worth of BAO observations, looking specifically for that predicted distortion pattern.
And did they find it?
They did. According to the research, they found a deviation from what we would expect from the standard model of cosmology, consistent with the distortion invoked by a local void.
Okay, so there is a distortion matching the void prediction.
Yes. And Bannock himself explains it. Let me see here. A local void slightly distorts the relation between the BAO angular scale and the redshift. Basically, the void's gravity slightly messes with the light traveling towards us, adding a bit to the redshift on top of the normal expansion effect. Redshift is how we measure cosmic speed and distance based on light stretching.
So the void acts like a subtle lens, making things look like they're receding slightly faster or slightly further than they would be otherwise.
That's a good way to put it. It's a slight but measurable gravitational effect on the light path, consistent with being inside this underdense region.
And how sure are they? Is this just a hint or something more solid?
Oh, it seems pretty solid, statistically speaking. The paper concludes their void model is, get this, about 100 million times more likely than a void-free model that tries to fit other cosmic data like the CMB.
100 million times. Wow, okay, that's not subtle.
Not subtle at all in statistical terms, and the practical impact. This research apparently reduces the Hubble tension from 3.3 sigma to 1.1 to 1.4 sigma.
Okay, can you translate the sigma part for us?
Sure. In particle physics and cosmology, sigma is a measure of statistical significance. A 3 sigma result is generally considered evidence, but 5 sigma is the gold standard for a discovery. The Hubble tension was stubbornly sitting above 3 sigma, which meant it was very unlikely to be just a fluke. Reducing it down to around 1 sigma, well, that means it's suddenly much, much more likely that there isn't a fundamental problem with our model, just this environmental effect, this void. It basically makes the crisis almost disappear statistically.
So it takes it from highly problematic discrepancy down to well within the bounds of possibility.
Exactly. It pushes it much, much closer to being resolved. A huge step forward.
Okay, this sounds incredibly promising then. But I see the research also notes, quite rightly, that this theory is going to require some rigorous testing. It's not case closed just yet.
Absolutely not. Good science always requires verification. The team is clear about that. They plan to embark on this testing regime. That means looking closely at other objects in our local cosmic neighborhood, different types of galaxies, other distance indicators, to see if their properties and movements also fit this picture of being inside a large void.
checking if all the local pieces fit the void puzzle.
Precisely. They need more data, more cross-checks, but the groundwork is laid. And it's worth mentioning, this isn't just some idea floated online. The research has been published in a serious peer-reviewed journal, the monthly notices of the Royal Astronomical Society, and presented at major astronomy meetings. So the scientific community is definitely engaging with it right now.
That's really exciting. So let's just recap the big picture for everyone listening. We've got this major cosmological mystery, the Hubble tension, this disagreement about how fast the universe is expanding that's been around for decades. And the solution might just be, well, that we live in a bubble, a giant region of relatively empty space, a cosmic void. It's kind of mind-bending that the solution to such a fundamental problem may at least partially be found in nothingness, as one source puts it.
It really is. And it leaves you with a pretty profound thought to chew on, doesn't it?
Yeah.
What does it really mean for how we see our place in the cosmos if empty space, or rather the distribution of that relative emptiness, plays such a crucial role in what we observe? How does knowing we might be in this giant void change how we try to map the universe and understand its grandest structures going forward?
It's a big question. Okay, imagine this for a second. You're just floating out there, deep space, and you look back,